Good morning, madam. My name is Meghana. I am from BTech third sem, branch Tribly, Institute of Aeronautical Engineering College, Dundigal, Hyderabad. Today, my topic is explain each block of operational amplifier block diagram. Introduction to operational amplifier. Operational amplifier are fundamental components in analog electronics. They are used for a variety of applications, including application filtering and signal processing. Understanding the block diagram is essentially for effective circuit design. Here we see the circuit design of operational amplifier. Inverting amplifier. This is the circuit diagram of inverting amplifier. They are used for a variety of applications, including amplification, filtering, and signal processing. Understanding the block diagrams is essential for effective circuit design and analysis. Block diagram overview. The operational amplifier block diagram consists of several key functions. Each block plays a specific role in the overall operation of the op-amp. Analyzing each component helps in understanding how the op-amp functions as a whole. Here is the block diagram of a typical operational amplifier. Input stage. The input stage is responsible for receiving the input signals. It typically consists of a differential amplifier that enhances the difference between the input signal. This stage is critical for achieving high input impedance and low noise levels. Differential amplifiers. The differential amplifier the voltage difference between two terminals. If rejects common mode signals, enhance the design signals integrity. This block is useful for applications where noise reduction is essential. Gain stage. The gain stage further amplifies the signal received from the input stage. It determines the overall voltage gain of the operational amplifier. This stage is designed to maintain linearity and stability in amplification. Output stage. The output stage drives the output signals to the load. It typically provides low output impedance to deliver power efficiently. This stage is crucial for ensuring that the op-amp can drive capacitive and resistive loads effectively. Feedback network. The feedback network consists of the output back to the input, defining the behavior of the op-amp. It stabilizes the gain and improves linearity by controlling the feedback factor. This is the circuit about the feedback amplifier, and it's also called feedback network. It stabilizes the gain and improves linearity by controlling the feedback factor. This network is essentially for achieve desired operational characteristics such as a gain and bandwidth. Power supply. The power supply provides the necessary voltage level for the operation of the op-amp. Dual properties, positive and negative, are typically needed to accommodate both positive and negative signal swings. Proper power supply design is critical for the linear operation of the op-amp. Load output. The output load refers to the component or a circuit connected to the op-amp output. This is the negative supply of the output load. Uh, it affects the performance, including output voltage swings and stability. Understanding load characteristics is essential for ensuring optimal operation of amp sleeve rate. This is the expressions, and we need to learn sleeve rate. It is the most important topic in this introduction. The sleeve rate is the maximum of the sleeve rate maximum rate of change the output voltage. It limits how fast the output can respond to rapid input signal changes. A higher sleeve rate is desirable for applications involving the high frequency signals. Ideal rectangular input waveform. This is the waveform of the sleeve rate. Common mode rejections ratio. It is also in short form CMRR. CMRR measures the ability of the op amp to reject common mode signals. A high CMRR indicates better performance in a noise environments. Understanding CMRR is important for designing analog circuits. This is the expression of CMRR. Resistors must match within 1 ppm. Measure CMRR. CMRR equal to delta V N. Feedback network. The feedback network connects the output back to the input, defining the behavior of op amp. It stabilizes the gain and improves linearity by controlling the feedback factor. This factor is essential for achieving desired operational characteristics such as gain and bandwidth. Power supply. The power supply provides the necessary voltage levels of the operational op amp. Dual properties, positive and negative, are typically needed to accommodate both the positive and negative signal swings. Proper power supplies design is critical for the linear operation of the op amp. Output load. The output load refers to the components or circuits connected to the op amp output. It affects the performance, including output voltages, swing, and stability. Understanding load characteristics is essential for ensuring optimal operation of op amp. Sleeve rate. The sleeve rate is the maximum rate of change the output voltage. It limits how fast the output can respond to rapid input signal changes. A higher sleeve rate is desirable for application involving high frequency signals. Conclusion of this topic is the operational amplifier is a versatile component essential in analog circuits, analog electronics. Each block in it diagram contributes to its functionality and performance. A thorough understanding of this block is vital for designing efficient and effective electronic circuits. Application of operational amplifier. Operational amplifiers are widely used in signals, conditions, filtering, and amplifications. They are integrally in analog computing, instrumentations, and control systems. Understanding their operational blocks aids in the effective application of op-amp in various circuits. Conclusion of this topic. The operational amplifier is a versatile component essentially in analog electronics. Each block, its diagram contributes to its functionality and performance. A thorough understanding of this block is vital for designing efficient and effective electronic circuit. Thank you.